Welcome back to Calculus 1. In the previous section, we learned to differentiate products and quotients, and we completed the basic trigonometric derivative rules. We now turn to functions built inside other functions. These are called composite functions. The chain rule lets us differentiate a composite function without expanding it or rewriting it in a completely different form. By the end of this lesson, you will be able to recognize the layers of a composite function and differentiate them from the outside in. Let's get started. Here is what we will cover in this lesson. First, we will learn to recognize when one function is contained inside another function. Next, we will use a chain rule to differentiate that combination. We will then apply the general power rule to powers, roots, and reciprocals. Finally, we will combine the chain rule with the trigonometric derivative rules from the previous lesson. The central idea is simple. Differentiate the outside, leave the inside unchanged, and then multiply by the derivative of the inside. Some functions are built in stages. One function produces a result, and that result becomes the input of another function. For y equals 3x plus 2 to the power 5, the inside function is 3x plus 2. The outside function raises the entire result to the fifth power. For y equals sine of 4x, the inside is 4x, and the outside is a sine function. For y equals the square root of x plus 9, the inside is x plus 9, and the outside is a square root function. The expression y equals tan squared x means tan of x is squared. Here, tan x is inside and squaring is outside. For y equals 1 over x minus 6, the inside is x minus 6, and the outside takes the reciprocal. Naming the inside and the outside before differentiating is the essential first step. Once the layers are clear, the chain rule becomes much easier to apply. The chain rule follows one consistent pattern. Differentiate the outside while leaving the inside unchanged, and then multiply by the derivative of the inside. If y equals f of g of x, then y prime is equal to f prime of g of x times g prime of x. The factor g prime of x is essential because it accounts for how the inside changes. Here, when x changes by delta x, the inside 2x changes by 2 delta x. The graph shows the effect at the origin. Over the same horizontal run, the tangent to y equals sine x rises 1, while the tangent to y equals sine of 2x rises 2. The slope is therefore doubled. That factor of 2 is the derivative of the inside function, 2x. Outside first, inside second, and multiply. Let's apply the chain rule to y equals 3x squared minus 5, all raised to the power 4. The inside is 3x squared minus 5, while the outside raises that entire quantity to the fourth power. First, differentiate the outside while leaving the inside unchanged. That will give us 4 times 3x squared minus 5 raised to the power 3. Next, differentiate the inside. The derivative of 3x squared minus 5 is 6x. Now multiply these factors. 4 times 3x squared minus 5 raised to the power 3 times 6x. After simplifying, the derivative is dy dx is equal to 24x times 3x squared minus 5 all raised to the power 3. We could expand the original fourth power, but that would create unnecessary work. The chain rule handles the same structure even when the exponent is much larger. The general power rule packages the chain rule for a function raised to a power. d dx of ux raised to the power n is equal to n times u of x raised to the power n minus 1 times u prime of x. Here, u of x represents the entire inside function. Bring the exponent down, subtract 1 from the exponent, and then multiply by u prime of x. This is not a separate idea. It is the chain rule when the outside function is a power. The rule also covers roots and reciprocals because a square root is a 1/2 power, and a reciprocal can be written with a negative exponent. When u of x equals x, then u prime of x equals 1, so the extra factor disappears and the rule reduces to the basic power rule from section 2.2. Here's an example. roots and reciprocals become straightforward once we write them as powers. For the square root example, rewrite the function as y equals the square root of x squared plus 7, rewrite that as y equals x squared plus 7 raised to the power 1/2. Apply the general power rule and multiply by the derivative of x squared plus 7. dy dx equals 1/2 times x squared plus 7 raised to the negative 1/2 power. This whole thing is multiplied by 2x. Thus, we're going to get the derivative equal to x divided by the square root of x squared plus 7. Because x squared plus 7 is always positive, this derivative exists for every real x. For the reciprocal example, move the denominator up as a negative power. That would be g of t equals negative 9 divided by 4t plus 1 squared would equal negative 9 times 4t plus 1 to the power negative 2. Now differentiate the outside and multiply by the derivative of the inside. This will give us g prime of t is equal to negative 9 times negative 2 times 4t plus 1 raised to the power negative 3 times 4. This will be equal to 72 divided by 4t plus 1 raised to the power 3. The original restriction remains that t cannot equal 1/4. Rewriting first avoids the unnecessary quotient rule. Now it's your turn to practice the chain rule with powers. For problem 1, the outside is a 6 power and the inside is 5x plus 2. For problem 2, we write the square root as a 1/2 power. For problem 3, we write the reciprocal as x squared plus 1 to the power negative 3. For problem 4, the outside is the 5th power and the inside is x cubed minus x. In every problem, differentiate the outside first and then multiply by the derivative of the inside. Pause the video now and work all 4 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, the outside contributes 6 times 5x plus 2 to the power 5, and the inside contributes 5. That would mean that y prime equals 30 times 5x plus 2 to the power 5. For problem 2, the 1/2 power and the inside derivative 4 combine to give y prime is equal to 2 divided by the square root of 4x minus 3. This would be for x is greater than 3/4. The original function is defined at x equals 3/4, but the derivative is not, because the denominator becomes 0 there. For problem 3, the outside contributes negative 3, x squared plus 1 to the power negative 4, and the inside contributes 2x. That would give us y prime is equal to negative 6x divided by x squared plus 1 to the power 4. For problem 4, differentiate the 5th power and then multiply by the derivative of x cubed minus x. That will give us y prime is equal to 5 times x cubed minus x to the power 4 times 3x squared minus 1. Each answer remains in factored form. Expanding would make the result longer without making it clear. The chain rule combines directly with the trigonometric derivative rules. If u represents the inside function, then d dx of sine of u equals cosine u times u prime. D dx of cosine u would equal negative sine of u times u prime. D dx of tan u would equal secant squared of u times u prime. And d dx of secant u would be equal to secant u times tan of u times u prime. The trigonometric derivative keeps its usual form, and the derivative of the inside becomes an additional factor. Cotangent and cosecant follow the same pattern, and the derivative formulas retain their minus sign. When the inside is simply x, then u prime is equal to 1, and these formulas reduce to the basic trigonometric rules from section 2.3. These three expressions look similar, but their structures are different. For y equals sine 2x, the inside is 2x and the outside is the sine function. dy dx is equal to 2 cosine 2x. For y equals sine squared 2x, the expression means sine of 2x is squared. Differentiate the square, then the sine, then 2x. That would give us dy dx is equal to 2 sine 2x times cosine 2x times 2, which is equal to 4 sine 2x times cosine 2x. For y equals sine 2x squared, the entire expression 2x squared is inside the sine function, and this would give us dy dx is equal to cosine 2x squared times 4x, which would be equal to 4x cosine 2x squared. The exponent in the middle expression applies after the sign. In the last expression, the exponent belongs to x before the sign is applied. Read the parentheses and exponent placement carefully before choosing the layers. Each example uses a familiar trigonometric derivative followed by the derivative of the inside. For y equals sine of 5x, the sine becomes cosine and the derivative of 5x supplies a factor of 5. That would give us dy dx is equal to 5 cosine 5x. For y equals tan x cubed, the tangent becomes secant squared, while the derivative of x cubed supplies 3x squared, giving us dy dx equals to 3x squared, secant squared of x cubed. For y equals secant 2x, the secant becomes secant times tangent, and the derivative of 2x supplies 2, giving us dy dx equals to secant 2x, tan of 2x. The factors 5, 3x squared, and 2 all come from differentiating the inside. Without these factors, each derivative would be incomplete. The trigonometric rule determines the main form of the answer, and the inside derivatives supply the additional factor. Now consider a function with 3 layers. Y equals cosine cubed of 5x, and this is the same thing as cosine 5x cubed. The outermost layer is the cube. Differentiating it gives us 3 cosine 5x squared while leaving cosine 5x unchanged. Next, differentiate cosine 5x. The cosine contributes negative sine 5x, and the inside 5x contributes 5. Multiplying all 3 factors gives us dy dx is equal to 3 cosine 5x squared times negative sine 5x times 5, and this would be equal to negative 15 cosine squared 5x sine 5x. Work from the outside toward the inside, one layer at a time. Each layer contributes the factor produced by its derivative. The chain rule often appears inside another differentiation rule. For f of x equals x squared times 2x minus 1 cubed, the function is a product, so begin with the product rule. The second factor then requires a chain rule. The raw derivative is f prime of x is equal to 2x times 2x minus 1 cubed plus 6x squared times 2x minus 1 squared. Both terms contain 2x and 2x minus 1 squared. Factor out those common pieces to give us 5 prime of x is equal to 2x times 2x minus 1 squared times 5x minus 1. The factored form makes the zeros of the derivatives easy to identify. X is equal to 0, x is equal to 1/5, and x is equal to 1/2. If we multiply the derivative out, those values would be much harder to see. Now it's your turn to apply the chain rule to trigonometric functions. For problem 1, differentiate cosine 7x and include the derivative of 7x. For problem 2, remember that tan squared of x means tan of x is squared. Differentiate the square first, then differentiate tan of x. For problem 3, keep x squared plus 1 inside the cosine after differentiating the sign. For problem 4, recognize 3 layers, the fourth power, the sine function, and 3x. Pause the video now and work all 4 problems, then continue when you are ready to check your answers. Let's check the answers. For problem 1, the cosine becomes negative sine, and the inside contributes 7. Y prime equals negative sine, y prime becomes negative 7 times sine 7x. For problem 2, the outside square contributes 2 tan of x, and the derivative of tan x is secant squared x. That'll give us y prime is equal to 2 tan of x times tan squared of x. For problem 3, the sine becomes cosine, and the inside contributes to x, giving us y prime is equal to 2x times cosine of x squared plus 1. For problem 4, the fourth power contributes 4, the sine contributes cosine 3x, and the inside 3x contributes 3, giving us y prime is equal to 12 sine cubed of 3x times cosine 3x. The final problem shows the full pattern. Each layer contributes a factor to the derivative. Let's bring them in ideas together. For y equals f of gx, differentiate the outside function with the inside left unchanged, and then multiply by the derivative of the inside. Y prime equals f prime g of x times g prime of x. For a quantity raised to a power, bring the exponent down, subtract 1 from the exponent, and multiply by the derivative of the entire quantity. When a function has several layers, repeat the chain rule from the outside in until every layer has been differentiated. Always identify the complete structure first. A product rule or a quotient rule may need to come before the chain rule, as it did in the previous example. In the next lesson, we will use implicit differentiation for equations that are not solved for y. The chain rule will be essential because y is itself a function of x. Thank you for watching. In this lesson, we learned to recognize a function inside another function and use the chain rule to differentiate the layers from the outside in. We applied the general power rule to powers, roots, and reciprocals, and we combined the chain rule with trigonometric derivatives. We also saw that the chain rule can appear inside the product rule when a function combines several structures. In the next lesson, we will use implicit differentiation to differentiate equations that are not solved for y. I'll see you there.